Okay, so we have a couple of examples where we apply the method of finding confidence intervals to an unknown population proportion. So remember, we estimate an unknown population proportion by taking a simple random sample of size n and finding the sample proportion p hat from the sample. So all the sort of structure of the development of the confidence interval for mu follows the same way for the confidence interval for p. We use a central limit theorem, and we get the C% confidence interval for p is p hat minus z star times what would be sigma over root n. This has one little wrinkle in it, and that is that the sigma for p hat, remember, was square root of p times 1 minus p, but when we're trying to estimate p, we don't know what it is, so we actually can't use that for sigma. So instead, we use the sample proportion to find or approximate the standard deviation for the standard deviation of p hat. So where we used to have a p times 1 minus p, we now have a p hat times 1 minus p hat because that's what we know. All right, the critical value has the same interpretation as before. The z star doesn't change. It's the point on the standard normal curve, or it's the z-score that captures the middle C% of the area under the standard normal curve. So here we wish to be 99% certain of we want a 99% confidence interval for the unknown population proportion p. We take a simple random sample of size 100. We discover the sample proportion p hat from those 100 sampled observations is 0.65. So we need to make our confidence interval. Now, 99% is not one of the cutoffs that the empirical rule tells us, so this comes from StatCrunch. And again, we will do some of this together, but we get not quite 3 because it's not quite 99.7%. So the z star here is 2.576 to capture the middle 99% of the area under the standard normal. That makes the margin of error 2.576 times the square root of 0.65 times 1 minus 0.65, which is 0.35, all over 100. So that margin of error, take a second, 0.65 times 0.35 square root divided by square root of 100 times 2.576. So if I manipulated my calculator correctly, I get about 0.123 for the margin of error. That makes the confidence interval p hat plus or minus 0.123. In other words, 0.65 minus 0.123, 0.65 plus 0.123. So 0.527 out to, what does that got to be, 0.773. So if I've done the arithmetic and the calculator correctly, we have a 99% confidence interval for the true unknown population proportion. So we're 99% sure that the true proportion of microchipped dogs is between about 0.53 and 0.77. Now that's a fairly wide range, right? Somewhere between 53% and 77% is not perhaps the most useful. And so similar to the average weight example, we can instead kind of think about how close we want to get and how sure we want to be, and from that figure out how many have to be in our study. so that's the setup for example 6, where we want to be 95% sure that we're within plus or minus 0.05 of the true proportion, which is another way of saying the margin of error has to be 0.05. So the 0.05, this is a little quick, right? Has to be z star times the square root of the margin of error. So this is the same as 0.05 equals the z star for the 95% is about 2, 1.96. Square root p hat 1 minus p hat over square root n. What I've done here is that the square root of a fraction is the square root of the numerator over the square root of the denominator. Now this one actually has a little complication that the previous example like this didn't have, and that is if we want to make any further progress we have to plug in p hat. But hold on, p hat comes from the study, right? We're trying to design the study. We want to know how many should be in our sample. So this is right before we've done p hat equals 0.65 in the last example. So it might kind of seem like we're stuck because we have to know the sample size to get the sample, to get the p hat, but we need the p hat to estimate the sample size. But we can do pretty well by plugging in what's called a conservative value for p hat, and that is 1/2. So a p hat of 1/2 actually makes this expression as large as it can possibly be. So this is going to tend to overestimate the number we need in the sample, but it's better to be sort of sure to have too much information than it is to have too little and miss your requirement. So here we're going to use p hat equals 1/2 as a way of getting around actually needing the p hat. So that's the square root of 0.5 times 0.5 over the square root of n. So 0.05 root n equals 1.96 times 0.5, because the square root of 0.5 squared is just 0.5. So root n, 1.96, 0.5 over 0.05. So that tells me that the square root of n, sorry for the handwriting there, but 1.96 times 0.5 divided by 0.05 is 19.6. So 19.6 squared is our requirement for n. That's about 384.1, so I round up to 385. So if we want to know the true proportion of microchipped shelter dogs, and we want to be 95% sure that we know that proportion to within 0.05, like the weight example, we're looking at a fairly large study. Not quite as bad, but sample 385 dogs, see if they're microchipped. That p hat will be a really good estimate for the unknown p. All right, so those are the examples I wanted to run through. We'll have a last brief video on getting StatCrunch to find critical values for us, and we'll run through a simulation that sort of emphasizes our lack of being 100% certain that a parameter is in a confidence interval. Right?